Welcome to the Orchestrate All the Things podcast. I'm George Anatiotis and we'll be connecting the dots together. What's a good enough weather prediction? That's a question most people probably don't give much thought to, as the answer seems obvious, an accurate one. But then again, most people are not CTOs at DTN. Lars Ewe is, and his answer may be different than most people's. With 100 meteorologists on staff providing weather predictions worldwide, DTN is the largest weather company you've probably never heard of. I hope you will enjoy the podcast. If you like my work, you can follow Link Data Orchestration on Twitter, LinkedIn, and Facebook.
Thank you for having me, George. So my name is Lars Ewe. I'm the CTO over at DTN. I joined the company about 2.5 years ago. Prior to that, I was running product and engineering over at Anaconda, which you're probably familiar with, which was also a very interesting job or opportunity. And prior to that, I was over at Click Security, which actually, no, eVariant was before that. I'm sorry. At eVariant, which is a healthcare company, was acquired by Healthgrades. In short, a lot of these jobs, what they have in common is this: I personally feel very strongly about data science, and just the ability to provide insights and help companies run their business more operationally efficiently and effectively by leveraging state-of-the-art technology to actually come to, and produce better outcomes. So DTN is in that regard sort of a logical evolution to my career. And I'm very excited to be here today and then talk to you a little bit about what we do here at DTN.
Great, thank you for the introduction. And to also share a few background on my side, a bit of background on my side as to the topic and what triggered, let's say, the conversation today. I was pitched a story by PR that had to do about the way that DTN engages in weather prediction. And I have to say that, initially, I have to admit that first of all, I wasn't familiar with DTN at all. But then, just looking around a little bit about what it does, I was somehow impressed by the fact that DTN is involved in weather prediction, because previously I was under the impression that this is a task reserved for state or government agencies, basically. Even though looking a little bit at what DTN does in general, and I'm sure you can enlighten us a little bit more on that. It started making more sense, basically, because it seems that having weather prediction, reliable weather prediction, is something that can be useful in those other activities that DTN is involved in. So that's the next thing I wanted to ask you, basically. So in what ways does DTN do weather prediction, and why it is useful, and for whom?
Absolutely. And if I may, maybe start the answer by a very quick high-level statement around DTN. As you said, not everyone's familiar with the company. So we are a global technology, data, and analytics company, and mostly active in agriculture, energy, and other weather-sensitive industries. And our main goal is to provide operational intelligence or actionable near real-time insights, if you want to call it that way, to our customers to help them better operate their business. So with that said, weather is a key ingredient in some of the data that we need in order to provide actionable insights. And yeah, you're right. There's obviously quite a few entities out there, both government and private, that are producing various weather forecasts and weather forecasting technologies. We are actually, depending on who you ask and how you count, one of the largest, not the largest, privately owned weather company in the world. We have more than 180 meteorologists on staff. We have hundreds of engineers, not just dedicated to weather forecasting, but to the insights and the operational intelligence products that I mentioned. And so we have a significant investment in weather and weather forecasting technologies. Now, you ask why. At the end of the day, we need global, consistent and reliable weather forecasting technology. And so a lot of the agencies, whether it's government agencies or other sources of forecasting data out there, are either not global or they have weaknesses in certain areas. They're also usually very restrictive in the resolution. So another thing that plays into the discussion is the quality of resolution in certain areas, right? And so what we have done is we are leveraging pretty much all of the above, all of these publicly available and sometimes through license proprietary data inputs. We're all using all of those. We also augment that with our own data inputs. We have and own thousands and operate thousands of weather stations worldwide. But most importantly, we have created a state-of-the-art ensemble engine that takes all of these various data sources and tries to, through the means of machine learning and other technologies, tries to improve overall predictive models globally with different and varying resolution using things like MPAS, but also by having various regional models that we run and adding them to the ensemble, so we can actually have the right data and the right resolution and the right quality for the right areas where we operate in and where we provide insights, if that makes sense, George.
Okay, I see. So first, before we get into the more technical details of the infrastructure that you use and the methods and the data that this infrastructure creates and how you integrate them all and how you use them to generate those predictions, I wanted to ask you if you can drill down a little bit on the specific products that DTN has around weather. If I'm not mistaken, I think I saw that the weather prediction is offered as a service in itself, but I think it also is used to power other services, right?
That is absolutely right. And in fact, the weather predictive services and APIs that we provide to our customers provide, in many cases, the core foundation of what we do. We do more than that, by the way. But really, where it gets even more exciting in our minds is the actual actionable insights, the operational intelligence we provide on top of that. So examples would be, we have a product called Storm Impact Analysis that actually helps utilities better predict outages based on storm systems passing through. And by doing so, allowing them upfront for planning better, staffing planning around that, meaning repairs and also avoiding some of the costs, regulatory costs and penalties that can come with outages, by having better understanding and insight into. So a lot of this, or maybe give you one more example, a lot of shipping would be another example where we actually help some of the largest shipping companies in the world guide and compute best routes for their ships, both from a safety perspective, but also from a fuel efficiency perspective, right? So oftentimes there's more than one benefit to these solutions that we provide. And aviation would be another example, by the way. But at the heart of all of this is really the idea of taking weather forecast technology and data that we have available, and then merging that with customer-specific data that is relevant to their operations, whether that's the location of ships or the hull shape of the ship, things of that nature, or whether it is outage information and the health of the infrastructure grid, the electric grid, for example, to then merge the data through machine learning models to help them provide these insights that are usually probabilistic in nature, which is also an interesting challenge in by itself, as you can imagine.
Okay, I see. So in the scenario where data, where weather prediction is offered as a standalone service, let's say, then I guess no further customization is needed except for the exact location that the client is interested in receiving weather prediction for. But in the scenario where that is used to power other services, such as the ones you mentioned, then I guess it's tailored specifically to the needs and the data, most importantly, the data of the customer. So it's not one common, let's say, service for everyone. It has to be tailored per customer.
That is correct. At least that's the highest level quality service we can provide. The more we can work with customers and integrate their data through standard common APIs that we provide, integration APIs and things of that nature, the higher the quality of service. The less data they provide, we can still provide more generic services in these areas. But yes, you're absolutely right. The quality of service of data that goes into the models and informs the models certainly also helps with the quality and the outcomes of the models.
Okay, okay. And as far as regards the comparison, let's say, of the kind of weather prediction that you do compared to standard, let's say, weather predictions offered by government service, let's say, where would you identify the main differences? Is it in granularity? Is it in time frame, or in scope, or in something else?
It really varies and depends, right? As you know, they all vary, and even the comparison baseline that you gave me, there varies in their own scopes and precision and so on. But yes, we obviously, as you would imagine, try to provide the right level of precision for the right areas that we operate in, and also for the use cases. So that's one thing. We also by creating an ensemble technology, and we have the ability to actually weigh the various models and through machine learning over time, use the right weight factor, the models that are more accurate in certain scenarios, given the scenario that you're trying to solve for. So really, it is it's a combination of in some cases we run very specific WRF models with high resolution in certain areas close to, say, harbors, where we need to have very precise weather information to safely guide ships in that area. In some cases, we actually use available data, but through ensemble technology, we try to compute and rely on the right or weigh the better models over time that are more precise for the scenario and the time frames, right? We also are looking at decades and decades worth of historical data that we have access to that obviously informs both our engine and our models, as you can imagine.
Okay. So let's then come to the actual infrastructure that you use. Disclaimer here, I'm by no means an expert in meteorology or weather prediction, but I have interviewed a couple of people in the past who are. So through them, I learned a couple of things. And as far as I can tell, it seems like satellite imagery is a very important data source in terms of weather prediction. But I think it's not the only one, right? So there's also input from sensors that gives you metrics such as humidity or rainfall, or other temperature, obviously, and other types of measurements that can be useful for the models. And well, potentially other sources that I'm missing as well. So I'm guessing you probably use these two. Does the company own its own satellite fleet, or do you get imagery from other people's satellites? And what other kind of data sources do you use?
Yeah, no, absolutely. You're right. There's many different observational data points that we use in forming our models and the forecast, therefore. Maybe not appropriate to go into all of our exact partnerships and license deals that we have, but we use data from various different sources, whether that is satellite data and imagery data, whether that is radar, whether that is weather stations. We even use oceanographic scatterometers, weather balloons, measurements coming from airplanes. There's a large array of different observations that are fed into the engine. And as you can imagine, by the sheer vast number of data, we're talking big data here. So in many regards, weather forecast at this age is really a big data problem. And it's also, to some extent, an Internet of Things data integration problem, where you're trying to, get access to all of this data and intelligently and smartly integrate the data and store the data for further processing.
Yes, indeed. And I imagine this is probably one of the most demanding tasks you have in your role because, well, of what you just mentioned, basically. So the sheer, not just the quantity and so the volume of the data, but also probably the speed at which this data is coming in. So you need to consume it really, really quickly, and also homogenize it and integrate lots of different data from different data sources in one common repository so that it can be useful for your models, right? And I'm guessing this is probably the part where AWS comes in, because again, in the initial storyline that was given, it was sort of framed around how you work with AWS to achieve that.
Yeah, no, absolutely, George. And maybe if I may, before we go into the AWS details, I think a little bit about Lars, but more importantly about this task. Um, it'd be interesting maybe for your audience to know, I myself am not a meteorologist either. I learned enough over the last 2.5 years that I can be dangerous enough to have this conversation with you. But we have, as I said, world-class meteorologists on staff and scientists. That's not me. But in order to build these kind of solutions, many different skills have come together, right? Whether it's the meteorologist and the science that we're talking about, whether it's the big data processing aspects, whether it's machine learning and data science know-how, DevOps. I mean, there's so many different things that all have to work hand in hand in order to provide solution. And that is really where I see my background. That's also where I see the company positioned, right? We excel at what we do by providing and having on staff talent in all of these areas, and by combining that know-how to build these solutions. If that makes sense, that really is something I wanted to mention. So back to your original question around AWS and how that plays in. There's a case study that is available if you just Google for AWS and DTN weather forecasting. There's a case study that goes into great detail for your audience if they're interested. But make a long story short, in summer of 2020, I believe, if memory serves me right, roundabout then, we actually decided to work very closely. We've always been an AWS shop, so a lot of our cloud compute happens in the AWS cloud. But we wanted to approach them because we came to realize that a lot of the high performance compute capabilities that we need for these kind of tasks weren't really served the best way, and also not the most cost effective way by the Amazon instances available at the time. And so by working very closely with them, we actually have, I mean, obviously most of the expertise or a good portion of the expertise comes from Amazon. So I don't want to misportray this and say DTN invented this. That would not be fair. But I will say DTN was a partner in developing this with Amazon. They developed the EC2 HPC 6A instance type, which is really a high performance compute node that is much more cost effective, higher throughput. But also more importantly, we work that in conjunction with parallel cluster, which you're probably familiar with, as well as elastic fabric adapter and the EFA protocol, FSX for Lustre. So there's various technologies that have to come together to actually allow for us to have parallel compute in a cloud environment with the interchange between the nodes, fast access to the underlying storage, the data storage, both read and write, to actually be able to get these throughputs. And in fact, we were able to more than double our capability of running these models from a capacity and timing perspective. And that leads us to the other aspect, right? Historically, weather forecasting, or not just historically, it's still an extremely compute intensive task, as you can imagine. And so not all that long ago, a lot of weather forecast systems were limited to, a very, fixed schedule, say 2 times a day. They would compute forecasts for 2 times a day. Not 4, 2 times a day, they would update the forecast and recompute. Well, that leaves a whole lot of gaps. And so we are now able to, thanks to all of these modifications, to do a couple of things. One is we're no longer scheduled on a fixed schedule for our forecast engine computes. We're now data-driven, and event-driven, which is really the goal, right? The ultimate goal is to recompute when you have significant changes in the underlying model, in the underlying parameters and data that justify a recompute. So we're now at that point where we can do that event-driven, which is very exciting. But more importantly, we can do so in an hour, and in many cases, we're starting to now see under 1 hour of update cycles in average, right? Again, it's data-driven. That's massive. The last number that I've jot down here, because I can't remember all the data always, is that at current state, we can create a 1 hour forecast, global forecast for the entire global grid forecast in under 1 minute with the latest AWS instances and the technologies that we have tried to develop. That is remarkable. And I think it gives you hopefully a good sense for sort of the innovation that's taking place in that space.
Yeah, it is. It is remarkable indeed. So, yeah, and thanks for sharing some of the background. So, if I got it right, basically you sort of worked together with AWS to co-develop new instances to better serve your needs. And I've seen it also happen in other use cases where basically when you have sort of edge cases, let's say, that are driving innovation in terms of whether it's data throughput or computational needs. And I guess in your case, it was probably both. So you sort of worked together with the people on Amazon's end to develop new instances, right? To better serve your needs.
Yeah, and I want to be very clear about the rules. Obviously, when it comes to compute infrastructure, no one is going to tell Amazon how to do that. That's where their expertise lies. But we certainly brought to the table and to the partnership our expertise around the models and around the data and around the requirements that we had, both from a just compute perspective, but also how to manage that kind of setup, etc. And so a wonderful partnership that was highlighted at their main event. But again, if anyone wants more detail, easiest is just Google up it's easy to find.
Okay. And so the other thing I was wondering is, I guess you're this is probably something you get asked by executives in your own company a lot, is whether this all still makes sense financially in a way. Because yes, I mean, I get how it's very important to be customer driven and event driven and all of that, but actually recalculating everything on on 1 hour per average interval, as you mentioned, it also incurs a significant computational and therefore financial cost for you. Does it still make sense to do that?
Yeah, no, it's a fantastic question. It's the side of the CTO job that isn't always the most enjoyable, right?
Mm-hmm.
We all enjoy the technology, we all enjoy innovation and producing new cool things. But you're absolutely spot on. We also have to make sure that the P&L makes sense and that there's a commercial component here that satisfies the needs, and it does. So again, just to be clear, there's complexity here that's probably past this podcast, but we recompute, intelligently based on what needs recomputation, right? We also have, again, varying degrees of precision on the grid based on regions in the world, customer base, and requirements that we have, right? So want to be very clear. There's because of what you just said, there is intelligence built into the solution and thoughtfulness as to the cost that occurs when recomputes happen. So very good point. Again, the part of the relationship with Amazon was not just better compute power and all the things we mentioned, but also to bring the costs down, to make it more cost effective, which plays into that. The other thing that's really interesting, for what it's worth, is as many companies out there, we also had, and speaking about expertise, we had more than 5, depending on how you count, forecast engines in the company. Through M&A, right? Through acquisitions of other companies, you bring in talent and you bring in technologies. And so, that was wonderful because that allowed us, that gave us a lot of IP and a lot of know-how, right? And we had learned through these previous exercises what works, what didn't work, the pros and the cons. But by consolidating all of that and building truly one global forecast engine, brought costs down significantly. So there's cost savings also just through integration and building and reducing some of the redundant runs that you had before across the business. Last but not least, I should mention that one of the things we take great pride in, this engine is not just for atmospheric, it's also for oceanographic. So really both marine and atmospheric is covered. And a lot of innovation is taking place as we speak, and the interplay between those two environments. That is still, we're still better learning and understanding that as scientists, and therefore as engines, we're still learning how to better model those interdependencies.
Mm-hmm. Great. Actually, that's precisely what I wanted to ask you next, about how exactly does this engine, does this model work in itself? Again, based on my previous exposure to the topic, I've kind of gathered that nowadays the way people do it is they sort of take a hybrid approach. So yes, learning from historical data and lots of machine learning, as you pointed out, but it turns out that domain knowledge is also very important. It gives you it gives you lots of nice properties to have in a system like that, like explainability and and the option to integrate knowledge that has that is formal, let's say, in equations and this type of thing that is, the formal side of meteorology that has been developed over the years. And I'm kind of assuming that this is it's the same approach that you're taking.
Yes, and you are not talking to the right person when it comes to the deep scientific background on this. That's not me, as I said
Yeah,
earlier.
yeah.
We have some of the industry-leading experts on staff doing exactly that. But you're right. It's very much a hybrid, right? There's a lot of different aspects that flow into the solution. As I said, there's a significant staffing proportion behind this, with varying different backgrounds. But what's interesting is, I think, we have seen with the sort of the ability of us as an industry to take on more and more data, to compute and parse data more effectively at larger scale. We have seen the ability to further and further improve our forecast capabilities because of that. There's another challenge here that, again, I'm not the best person to talk to all the exact details, but um, the nature of weather forecasting historically has been deterministic, but often with failure, right? I'm trying to tell you that it's going to be this temperature, this humidity, and these wind parameters and whatever else at a certain time in a certain location. And as we all know, sometimes it hits it on the spot, sometimes not quite so much.
Yeah.
So the trick becomes more and more to make that actually a probabilistic forecast, because that's really what matters from an end user perspective. One of the big aspects that I always stress with these kinds of discussions is weather in it by itself, while interesting, intriguing, isn't really the main problem you're trying to solve for, right? You're really trying to make decisions upon that, right? So given certain weather conditions, should I or should I not evacuate this offshore drilling facility? Should I not prevent this sports event to take place? Should I not reroute my ship or my airplane? And as you can imagine, the probabilistic nature is what comes to mind, right? It'd be nice to know how probabilistic certain outcomes are, so you can further factor that into your risk equation, so to speak. That's another area where we're doing a lot of research right now in this ensemble technology by, and again, I'm not the expert to be honest here, but by providing a different way of how these different forecast parameters, and also the different models that we have, how they actually all get ensembled together, and by doing so, providing a more probabilistic outcome reporting mechanism is something we're working hard at, and hopefully we'll have more to report over time.
Mm-hmm. Yeah, and if I may add from the consumer, let's say, point of view, I've noticed that over the last few years, it seems that the weather forecast that you get as a consumer, again, they also incorporate the probabilistic element as well. So they don't anymore tell you like, okay, tomorrow is going to be a thunderstorm, for example. You get a more probabilistic prediction, like there's a heavy probability of a thunderstorm, something like that. So I guess the broader audience is also getting more acquainted with this type of prediction. And you already kind of mentioned some of the things you're working on, let's say, in the for the immediate future. And hearing you mention things like ensemble models and integrating different engines, it's also sort of hinted to one of the closing questions I had for you, which was, I imagine that in order for those models to be good enough, basically, they have to be quite specific in terms of the region that they're modeling. So you probably have a different model, let's say, for Africa or Europe, and even specific specific areas within each continent. So I wonder if those models are somehow integrated with each other, and whether there is a sort of meta model, let's say, that you potentially have to build in order to have better granularity in the overall prediction. And if this is something that you're working on, and to give it a little bit more grounding, it sort of made me think of the digital twin approach, and something that I've seen NVIDIA, not just me, but actually something that NVIDIA has published recently with the so-called Earth 2. So they're basically building a model of the entire Earth. And I wonder if this is a direction that you are taking as well.
We absolutely are interested in learning, and also are dabbling in some of these areas as well. As I said, there's work being done at DTN, active work to better understand marine and atmospheric interactions, which is the same principle, right? How do some of these systems interact with one another? You're absolutely 100% right. We run different models in different regions with different resolutions. We are also, as part of this, making more and more use of MPAS, which, if you're not familiar, is a model that is actually variable, where you can have a global model, but you can configure it with different variable precision in different regions. So if you're in the middle of the desert with little to no population and little to no commercial relevance, potentially, you might have a higher resolution, a lower resolution there, whereas, or you get the picture. So we're doing that. And again, the trick with Ensemble is to actually try to learn from all of these models and pick and choose in an automated fashion the right models and with the right weights and the right circumstances. And there's a feedback loop where we're that's self-training, right? It's constantly evolving to provide better outcome. But you said another word that I have to comment on, because it's an internal discussion that makes me laugh a little. You said good enough.
Mm-hmm.
And the reason I laugh a little, George, is because that's, as you can probably imagine, that's sort of the ongoing dialogue between the business side, as you mentioned earlier.
Yeah.
There's a business side to this, and the scientific side. And one thing to always keep in mind here is that there's a lot of downstream consumption where the real true value lies in our minds, right? Again, should you or should you not take certain action as a business as a result of this? And it so turns out that oftentimes you want to be very careful in how you balance your investment levels, so to speak, because the weather is just the input parameter for the next downstream model, right? And sometimes that extra half degree of decision may or may not even make a difference for the next model down, right? And sometimes it does. And so that's why this whole discussion is a non-trivial discussion, to be honest with you, because there's a lot of discussion that needs to take place in the configuration of these systems and the evolution of the systems relative to the use cases you're trying to satisfy and the actual business problems you're trying to solve, which again isn't so much just the weather forecast, but is what does that weather forecast mean to your operations as a business licensing our solutions and our technology.
Yeah. I'm sure that's a very fine line to walk, because, well, obviously, scientists and the people who build those models would be happy working to even gain marginal improvements, but that doesn't always make sense in the broader, in the bigger picture, let's say. So I guess this is where people like you come in and sort of try to balance things.
Yeah, and to give our staff some credit, I think the dialogue that we had over the last 2.5 years around this topic has been phenomenal. And I think more and more do I even see the science teams and the engineering teams appreciate the commercial aspect of this, right? And in fact, I think wasn't that long ago where I was in a meeting and someone said, "But wait, is what about good enough? Shouldn't that be good enough?" And as you can imagine, I had to laugh a little. I was like, "Yes, now we're all getting on the same page." So it's a very key ingredient for any business. Doesn't matter whether it's weather or anything else, is to make sure that it's financially and commercially viable, and then you're actually producing something where you don't over optimize on one component or subcomponent, right? That's true for, I guess that's true for pretty much anything we do as a society, but certainly applies here as well.
Yeah. And yes, it's well, everybody has their role to play, and I guess yours is kind of, again, looking at the big picture and stepping in when you have to.
And George, if I may, one thing that just came to mind that I'd like to add, if I may, is with respect to digital twins. I think they're actually extremely relevant in many different ways, right? They're relevant in the way that you just alluded to, but we're also looking into and investing heavily in digital twin technology around, say, for example, ships and how a digital twin of a ship behaves under certain weather conditions, wave patterns, etc., right? So that we can better compute and predict the route, but also the timing, right? part of what is equally important with shipping, for example, is to know exactly how much delay or when the ship can arrive at a certain location. Well, that has to do, is dependent on the type of ship, the hull shape, the quality of it is in, meaning, maintenance aspects and things of that nature. So digital twins play into many of these solutions in many different ways, if that makes sense.
Yeah, it makes sense that since you have a variety of services that you offer to for a variety of scenarios, then it would make sense to model some key concepts in that, like ships or planes or I don't know, ports and so on. So yes, it does make sense. Great. Thanks a lot for your time and for the conversation. It seems like you're doing some interesting work over there. And yeah, I guess the one of the key things that comes out of this conversation is that, well, weather really is a sort of substrate service, let's say, that is consumed by a lot of other of your services, and by extension, I guess that that sort of mirrors how things work in the real world. So you have to know what the environment is like to be able to plan and respond accordingly. I hope you enjoyed the podcast. If you like my work, you can follow Link Data Orchestration on Twitter, LinkedIn, and Facebook.